much. So this is going to be the first part of a two-part talk. It's going to be on some joint work with Dennis Gatescourt, who will tell you about some joint work in the second hour. In this first talk, I'd just like to introduce the context for that work. I want to talk about Bayes' conjecture on Tamagawa numbers and where it came from. So let me start by reviewing something very classical, the Siegel mass formula for quadratic forms. So by a quadratic form, I'm just going to mean a homogeneous quadratic polynomial in some number of variables. So here are some examples of quadratic forms in two variables. X squared plus y squared, x squared minus y squared, minus x squared minus y squared, and so forth. So one of the basic questions you can ask about quadratic forms is whether or not they're equivalent. Meaning, is there a linear change of coordinates that can convert one into another? So the answer to that question will depend on what ring you're working over. So these quadratic forms here, these are defined over z. The only coefficients I've used are integers, plus or minus 1. These, as quadratic forms over the complex numbers, they're all equivalent to one another. Because if I multiply x by I, it changes x squared to minus x squared. But over the real numbers, they're not equivalent to each other because, for example, this quadratic form here is positive definite. This quadratic form over here is negative definite. And this one in the middle is indefinite. It takes both positive and negative values. So these can't possibly be equivalent over the real numbers. And in particular, they can't possibly be equivalent over the integers. Let me add one more example to this. Take x squared plus 3y squared. So here's another quadratic form over the integers. And over the real numbers, these two quadratic forms here are equivalent to one another because I can multiply y by a square root of 3. And that'll change this expression up here to this expression down here. But over the integers, they're still not equivalent. And one way you can see that is to see what happens when you reduce modulo 3. Modulo 3, the 3y squared will go away, and this quadratic form here will become degenerate. But x squared plus y squared is non-degenerate modulo 3. So these are not equivalent mod 3, and therefore they can't be equivalent over the integers. So I've given you two ways that you can tell quadratic forms over z apart. One is to look over the real numbers. Over the real numbers, the classification of quadratic forms is fairly simple. A non-degenerate quadratic form over the real numbers is determined by the number of variables and its signature. And another way you could try to tell quadratic forms over z apart is by reducing them mod 3, or reducing them mod 4, or reducing them mod 5, and trying to tell if those quadratic forms are equivalent. And that's at least a finite problem, because there's finitely many linear changes of coordinates you could test. So that motivates the following definition. So two quadratic forms q and q prime, I'm always going to assume they're in the same number of variables. They're quadratic forms over z, which for simplicity I'll assume to be positive definite. We'll say they are in the same genus. If q is equivalent to q prime mod n for every integer n greater than 0. So modulo n for any n, we can find a linear change of coordinates that converts q into q prime. So it's clear that if we have quadratic forms that are equivalent over z, then they must be in the same genus. And you can ask, does the converse hold? That is, if you have two quadratic forms which are not equivalent over z, can you prove that by some combination of the methods that I described a second ago? So the answer to that question turns out to be no, but almost yes. If you fix a quadratic form q and ask about quadratic forms that are in the genus of q, up to equivalence there are only finitely many. And in fact, there's a formula which tells you how many, which is called the Siegel mass formula. So before I can state that, I need to introduce a little bit of notation. So let's say that q is a quadratic form over some commutative ring R in n variables. So I'm going to write OQ of R, the orthogonal group of Q. This is the set of n by n matrices, linear changes of coordinates, which preserve the quadratic form Q. So for example, if R is the real numbers and Q is the standard quadratic form, which is the sum of the squares of the coordinates, then this is the usual orthogonal group of rigid motions of Euclidean space. On the other hand, if Q is a positive definite quadratic form over the integers, then it's rigid motions that preserve a lattice inside Euclidean space. And that's always going to be a finite group, because for any particular lattice vector, there are only going to be finitely many other lattice vectors that have the same norm. So over Z, if Q is positive definite, this group will always be finite. So now I can state for you the Siegel mass formula. So let Q be a positive definite quadratic form over Z. Well, you take the sum over all Q prime in the genus of Q up to equivalence of 1 over the size of that automorphism group, 1 over the cardinality of that finite group, which preserves the quadratic form Q prime. And the Siegel mass formula tells you that this sum is equal to something else. Now, you don't need to work very hard if you want to prove that. But you can do better. It's equal to some specific other thing. I'm not going to tell you what that is in general, but let me just tell you what it is in the simplest possible case. So the simplest possible case is when we consider unimodular quadratic forms. So definition, if Q, a quadratic form Q over the integers is unimodular if Q is non-degenerate modulo P for all prime numbers P. So a couple of non-obvious things about unimodular quadratic forms. First, this is actually a very strong condition. So if you're talking about positive definite quadratic forms, if they're going to be unimodular, the number of variables always has to be divisible by 8. Another non-obvious thing is that if you fix the number of variables, then unimodular quadratic forms comprise a genus. That is, any two unimodular quadratic forms belong to the same genus. They must be equivalent mod n for every n. So an example to which you could apply this formula is to the unimodular genus. So let me tell you what this says in the case of unimodular quadratic forms. So let's take the sum over all Q prime unimodular up to equivalence. And now the right-hand side, well, it's got some power of 2, and it's got some factors of pi, and it's got some special values of the gamma function, and it's got some special values of the Riemann zeta function, and I'm missing one. You get the idea. It's some wild expression that, well, if you're not used to thinking about special values of the Riemann zeta function, you might wonder, is that even a rational number? Well, if you are experienced in thinking about special values of the Riemann zeta function, you might just rewrite this instead as a product of Bernoulli numbers. And then it's obvious that it's rational, but it's not obvious that it solves a counting problem. So this is what the Siegel mass formula says. Let's see some examples. So I said the number of variables always has to be divisible by 8. So the simplest example you might try is n is equal to 8. And then you can evaluate the right-hand side. And the right-hand side turns out to be 1 over 2 to the 14th times 3 to the 5th times 5 squared times 7. So in particular, the right-hand side is non-zero, which means there's at least one unimodular quadratic form of in 8 variables. And there's one that you can write down, where the corresponding lattice is the E8 lattice. It's the root lattice of the exceptional Lie group E8. And the automorphism group of that lattice, it's the Weil group of E8, and it's a group of exactly this order. So that tells you that one of the terms on the left-hand, in this sum on the left-hand side, is equal to the right-hand side, which means that there can't be any other terms on the left-hand side. So the Siegel mass formula, the formula implies that the E8 lattice is unique. It's the only unimodular quadratic form in 8 variables. So lest you be tempted to think that this equality is an equality between numbers that look fairly small, let's consider n equals 32. Well, in this case, the right-hand side is approximately 40 million. And, well, the left-hand side is a sum of terms, and each of those terms is at most 1. So if that sum is going to be around 40 million, that means there's got to be a lot of terms. So in this case, the Siegel mass formula tells you you're never going to classify unimodular quadratic forms in 32 variables. It tells you there exists millions and millions of inequivalent unimodular quadratic forms. All right, so what I'd like to do now is tell you a little bit about a way that you can think about this formula, following a reformulation of it, following ideas of Tamagawa and Wei. So I told you that 2 quadratic forms in the same genus, they don't have to be equivalent, but let's try and prove that they are. We're not going to succeed, but by trying, we'll maybe get an idea of how many there are, which is what the Siegel mass formula is about. So let's suppose that Q and Q prime are in the same genus. So what does that mean? That means that for every integer n greater than 0, Q is equivalent to Q prime modulo n. So I can write Q is Q prime composed with A sub little n, A sub big N, where A sub big N is an n by n matrix over Z mod big N. So here, little n is the number of variables. Okay, so there is such a matrix A sub n. That's what it means to be in the same genus. And of course, there's only finitely many choices for what this matrix could be. And then a simple compactness argument will tell you, all right, you can choose all of these A sub n's to be compatible with one another. That is, so that, for example, A sub 2n reduces to A sub n when you reduce modulo n. So choose these compatibly. We can think of this collection of all these matrices A sub n as giving you an element in GLN of the ring Z hat. So here, Z hat, I mean the profinite completion of Z. It's the inverse limit of the ring Z mod n as n ranges through all the positive integers. Or by the Chinese remainder theorem, there's another way that you can write this write Z hat. You can write it as a product over all primes P of the ring of p-adic integers. So let's call this matrix A. And then we learn that Q and Q prime, they're equivalent over the ring Z hat. So Q is Q prime composed with A. This is now a linear transformation over the ring Z hat. So maybe they're not equivalent over Z, but they're definitely equivalent over Z hat. And therefore, they must be equivalent over the p-adic integers for every prime number P. All right. Well, this tells me that Q is equivalent to Q prime over the p-adic rationals for every prime number P. So here the p-adic rationals means the p-adic integers adjoin P inverse. And also, Q and Q prime are equivalent over the real numbers, because I said from the beginning that I only wanted to consider positive definite quadratic forms. So the p-adic rationals and the real numbers, these are all the different completions of the field of rational numbers. And a non-trivial theorem tells you that these two conditions together imply that Q and Q prime are equivalent to one another over the field of rational numbers. So this implication, definitely not obvious. This is the Hasse principle for quadratic forms. Principle. All right, so what does that mean? That means that we can write Q as Q prime composed with B, where B is some n by n matrix over the rational numbers. All right, so let's combine these two facts. So Q is Q prime composed with A, and I can write Q prime as Q composed with B inverse. So Q is Q composed with B inverse composed with A. So what does that tell us? We have something that lies in the orthogonal group of Q. We have a linear transformation that preserves the quadratic form Q, namely this expression B inverse A. So this lives in OQ, but of what? Well, A is a matrix with coefficients in Z hat, and B is a matrix with coefficients in the rational numbers Q. And if I want to multiply them together, I have to enlarge both of those rings. So let A fin be the ring of finite adeles. This is just the tensor product of Q with Z hat. And there's an expression like this for A fin. You can think of this as sitting inside the product over all P of QP, but it's not the entire product. It's the so-called restricted product, where almost all the coordinates belong to ZP. So this matrix here belongs to OQ of the finite adeles. Now, this depends on some choices. In order to produce this element, we needed to choose an isomorphism of Q and Q prime over Z hat, and we needed to choose an isomorphism over Q. So this matrix A that we chose, it might not be unique, but it's unique up to multiplying on the right by linear transformations that preserve the quadratic form Q. So this product, this is ambiguous, but up to right multiplication by elements of OQ Z hat. And similarly, we had to make a choice of B. That's unique up to right multiplication by elements of OQ of the rational numbers. So what we really have here is something that's a well-defined element of this set of double cosets. OQ of the finite adeles mod on one side by OQ of Z hat, and on the other by OQ of the rationals. And that's now independent of choices. So what can we say about this double coset? What would it mean for this to be the identity double coset? Well, that would mean that we can choose A and B so that A is equal to B inside this ring OQ of A of the finite adeles. So the coefficients of A are simultaneously belonging to Z hat and to Q. But the intersection of Z hat and Q inside that tensor product is just the usual ring of integers. So this is going to be the identity coset if and only if we can find a transformation that converts Q into Q prime over the integers. So if you elaborate on that argument, what you learn is that this collection of double cosets is exactly the collection of equivalence classes of quadratic forms that are in the genus of Q. So if you ignore the fact that we're throwing in these factors here, what the Siegel mass formula is about how many double cosets there are. So that's what we want to figure out. But before we do that, I want to modify the question in two ways. It's going to be convenient to work not with the full orthogonal group here, but with a subgroup, namely the special orthogonal group. Let's throw in the condition that the determinant of A is equal to 1. So let me replace this collection of double cosets by replacing the orthogonal group by the special orthogonal group everywhere. So that's not the same set. It's not the same counting problem, but it's not far off. At the end of the day, this replacement is going to end up modifying what we've done by an overall factor of a power of 2. So let's try and figure out how many cosets there are here. The other modification that I would like to make is to work with the full ring of adeles rather than just this ring of finite adeles. So the full ring of adeles is defined to be the product of the ring of finite adeles with the real numbers. So let me erase this fin here. That has the effect of making this group in the middle a lot bigger. It multiplies by SOQR. And I'll just cancel that out by dividing on this side by SOQR. So this maneuver has no effect on what this collection of double cosets is. All right, so why have I made these maneuvers? Well, this ring of adeles has some very convenient properties. First of all, it's a topological ring. And its topology is locally compact. So SOQ is a group of matrices over the adeles that inherits a topology, and it's a locally compact group. So SOQA, let me just say, this is locally compact. And inside that sits the group SOQ of the rational numbers, and that's actually a discrete subgroup. So this is discrete. And on the other side, we have this group here. Let me write this as SOQ of Z hat cross R. This is a compact open subgroup. So now I want to analyze this using tools from the theory of locally compact groups. So in particular, any locally compact group has a left invariant measure which is unique up to scaling. So let me denote such a measure by mu. So mu, I can think of it as a measure on SOQ of the adeles, but it descends to a measure on the quotient of SOQ of the adeles by this discrete subgroup. So let's consider just the set of left cosets, SOQ of the adeles modulo SOQ of the rational numbers. And this is acted on by a compact group, namely SOQ of Z hat cross R. And the cosets, we're trying to count how many double cosets there are. Those can be identified with the orbits of this group action. So we can ask, what's the measure of this quotient, SOQ of the adeles modulo SOQ Q? And roughly speaking, it's the number of cosets times the measure of this group that's acting. Now that's not quite right because this group doesn't act freely. So what I can say is that this is a sum over orbits of 1 over the size of a certain stabilizer group. The stabilizer group of, if I pick an element here and look at its stabilizer in this group, well, that's always going to be a finite group because it's as a subgroup of SOQ of the adeles, it must be both discrete and compact. So 1 over the size of certain finite groups. All right, but I told you that the double cosets can exactly be identified with quadratic forms Q prime that are in the genus of Q. So let me write this as a sum of quadratic forms Q prime. Oh, and I'm sorry, that numerator is not 1. It should be the measure of the group SOQ Z hat cross R. And then what does that finite group come out to be? If you unwind the definitions, it's exactly, well, the analog of what we had over there, namely, it's the size of SOQ prime of Z. Linear transformations that preserve the quadratic form Q prime and have determinant 1. All right, so we could rewrite that. Let's just, if we take the sum over Q prime, 1 over the size of SOQ prime Z, what we're saying is that this is the measure of SOQ of the adeles modulo SOQ Q divided by the measure of SOQ Z hat cross R. So everything that I've said is good for any invariant measure that we choose. Invariant measure is unique up to scaling, and of course, scaling mu will change the numerator and denominator, but it won't change the quotient here. So the next idea is that actually for this particular locally compact group, and locally compact groups that look like it, there's a canonical way to choose a Haar measure. There's a canonical choice of Haar measure, which is called Tamagawa measure. So I want to tell you about that canonical measure. So let's think about SOQ of the adeles. What does it look like? Well, it looks like SOQ of R cross, and it's essentially then a product over all P of SOQ of the p-adic rationals. But strictly speaking, it's a restricted product where you can have denominators only finitely many times. So as a first step to defining a Haar measure on this big product, let's just think about defining a Haar measure on this group here. So as I told you before, this is just the usual special orthogonal group of rigid motions of Euclidean space. It's a compact Lie group of finite dimension. So to define a left invariant measure, on SOQ of the real numbers, well, you can choose a left invariant differential form of top degree. So the collection of left invariant differential forms of top degree on this Lie group forms a one-dimensional vector space over the real numbers. So let me call that vector space V sub R. And any non-zero vector in V sub R defines for you a left invariant measure on the group SOQR. Well, that doesn't help much because choice of an element of a non-zero vector space is still ambiguous up to scaling. But now this group SOQR, it's not just any Lie group. It comes to you as an algebraic group. It comes to you defined as the collection of matrices that satisfy certain polynomial equations. And moreover, the polynomial equations only use coefficients in the rational numbers. So this is actually an algebraic group, and it's defined over the rational numbers. And a consequence of that is that inside this one-dimensional real vector space of left invariant top forms, there's a one-dimensional rational vector space of left invariant differential forms that are defined over Q. And again, any non-zero vector in here gives you a non-zero vector in here, and therefore it gives you a measure. All right, that cuts down on the ambiguity a little bit, but there's still a lot left. So let's think next about what would happen if we took one of these other factors, SOQ of the p-adic rationals. So this is not a Lie group in the usual sense anymore. but it's what's called a p-adic analytic Lie group. And the story is similar. In order to define a left invariant measure on here, well, you can get one if you have a left invariant differential form of top degree. And those form a one-dimensional vector space, but now over the field QP of p-adic rationals. But again, this is not just any p-adic analytic Lie group. It comes to you from an algebraic group defined over Q. And therefore, sitting inside this vector space of all left invariant top forms, there's a rational subspace consisting of left invariant top forms that are defined over Q. And in fact, that's the same rational vector space that appeared here, because it's the same algebraic group over Q that gives rise to both of these completions. So the upshot of this is that if you choose a non-zero element in this rational vector space VQ, let's choose some element omega in here, not equal to 0, well, it gives you a measure on each of the factors that appear in this product decomposition. It gives you a differential form on each factor, which you can turn into a measure. So you could then define a measure on SOQ of the adeles by, roughly speaking, multiplying all those measures together. Now, a priori, you might think that depends on the choice of omega. But let's see what happens if we were to change omega. What happens, for example, if we multiply omega by -5? Well, if you look over the real numbers, you have a differential form of top degree on a Lie group, and then you multiply it by -5, the corresponding measure gets multiplied by the absolute value of -5. It gets 5 times bigger. Now, if you look over QP, the situation is exactly the same. The only difference being you're not supposed to use the usual absolute value of -5. You're supposed to use the p-adic absolute value of -5. So that means if p is not equal to 5, multiplying by -5 won't change the measure. The only exception is when p is equal to 5. And in that case, you multiply by the 5-adic absolute value of -5, which is 1/5. So the 5-adically, the corresponding measure gets scaled down by 5. Once you've multiplied all these measures together, those two factors of 5 cancel out, and you find that the measure that you've defined on this group is actually independent of omega. So that canonical measure is called Tamagawa measure. So let's just go back to this statement here and rewrite it using Tamagawa measure. I'll denote it by mu Tam. All right, so why does this help? Well, now the denominator is something that you can explicitly evaluate. Just choose this differential form omega, and now, well, this group here is not a restricted product, it's just actually a product of SOQ of the real numbers times a product over all primes p of SOQ ZP. So first you have to take omega, that gives you a measure on this compact Lie group, and you do an integral. And you might imagine that if you were to do that integral, it would be something that you could write in terms of pi's and gammas and so forth. And then you have to figure out the volume of all these other factors, and that's essentially a counting problem that you have to think about mod p for every p. You solve all those counting problems, and you multiply all the answers together. So that should be something that has some kind of Euler product expansion, and maybe something that you would expect to see some Riemann zeta functions appear. So it turns out that all of the complicated bits of this expression come from the denominator here, and you can rewrite the Siegel mass formula in a way that you can actually remember. So the Siegel mass formula reformulated is just a description of the numerator of this expression. It says that the Tamagawa measure of SOQ of the adeles mod SOQ of the rational numbers is equal to 2.
3 or more variables.
What's that?
3 or more variables.
3 or more variables. I should be careful because this is not a semi-simple group when there's 2 variables. All right, so That's good. But how good is it? Maybe there's still this mysterious number on the right-hand side. Where does the number 2 come from? Well, the number 2, it turns out, comes from the fact that the special orthogonal group is not simply connected. Instead, it has a simply connected double cover, which I'll call spin Q. And you can do exactly the same story with spin Q. You can define a Tamagawa measure, and if you take spin Q of the adeles mod spin Q of the rational numbers, this ends up having measure equal to 1. So motivated by this and several other examples, they proposed a generalization. So let me call this We's conjecture. So let G be a semi-simple, simply connected algebraic group over Q. So this is all we need in order to run that story I gave you about Tamagawa measures earlier. You can look at G of the adeles. This is a locally compact group, and it has a canonical Haar measure, which I'll call mu Tamagawa. And in particular, you can ask, what is the measure when you divide out by this discrete subgroup G of Q? And the conjecture is that this should always be 1. So this is now a theorem. Theorem of Kottwitz building on work of Langlands and Lai. So this is true for any semi-simple algebraic group over Q, and it's also you can replace Q here by any number field. But what I want to talk about is what happens when you replace Q not by a number field but by a function field. I want to talk about the function field analog of this conjecture. So now I need to reboot a little bit just to introduce some notation for working over function fields. So now instead of Q being a quadratic form, Q is going to be a power of a prime number. And FQ is going to be a finite field with Q elements. And X is going to denote an algebraic curve over FQ. And Kx is going to be the fraction field of X. So if you don't like the theory of algebraic curves, you can imagine that X is a projective space over FQ, and then this field Kx is just the field of it's just the fraction field of the polynomial ring on one generator T. And everything I'm going to say is interesting even in this case and reduces to this case with a bit of effort. Okay, so the idea is, well, maybe I should just recall for you the dictionary by which you should think of this as analogous to the kind of questions that we were just discussing. So the field Q is analogous to this fraction field Kx. And prime numbers P are analogous to closed points little x inside this algebraic curve. And now the analog of, say, the p-adic integers over on this side is the completed local ring of x at the corresponding closed point. So this is a complete local ring, which I'll write as OX. And this is always non-canonically isomorphic to a polynomial ring in one generator over a finite field. So these are, once you choose a local generator. local coordinate at the point x. So the analog of these fields QP, well, QP is the fraction field of ZP, and the analog of this is, I'll write as KX, which is the fraction field of OX. And finally, the analog of this ring of adeles is the restricted product of all of these fields Kx. That means the subset of the product where almost all coordinates belong to this ring OX. So this I'm also going to denote just by A for the ring of adeles. And so how close is this analogy? Well, A is again a locally compact ring. And so if you have an algebraic group that's defined over Kx, then G of A has the structure of a locally compact group. So let's suppose that we're in that situation. So let's suppose that G is a simply connected, semi-simple group which is defined over this field Kx. Well, you can run the definition of Tamagawa measure again. There's a canonical measure that you can define on the group G of the adeles. And G of the adeles contains G of the fraction field Kx as a discrete subgroup. And you can ask, what is the measure of this quotient? And the function field analog of We's conjecture would say that this should be equal to 1. So now what I want to do is just take the whole lecture that I gave up to this point, which was starting with the Siegel mass formula and reformulating it as a nice-looking statement about the volume of some adelic quotient, do it all in reverse. Let's take this nice, clean-looking statement and transform it into something that might look a little more complicated, but is concrete in that it's saying that it describes the solution to a counting problem. So in order to do that, I want to take this and mod out on the other side by some compact subgroup of G of A. So to do that, I need to assume a little bit more. Let me assume that G is not an algebraic group over Kx, but a group scheme over X, or a family of algebraic groups that's parametrized by X. And
Does it also follow from Potter's?
what's that?
Is the statement also Potter's theorem? In the functional field case, is it also?
I don't think so. So
What was the question?
the question is this a theorem in the function field case also by the same argument? And I believe that these parts of the arguments go through in the function field case and that this one does not.
The language and lines, the theory lies not going to be. But this part we will say the trace formula in this one. That's very important. So I think in the anisotropic case, that's the hard thing.
All right, so where was I? Right, so let's assume that we have not an algebraic group defined over Kx, but really a family of algebraic groups parametrized by X. I might not be able to arrange that that's semi-simple at all points, but I can at least arrange that all the members of that family are smooth and connected. And then it makes sense to consider the product over all x of G of OX. And this sits inside G of the adeles as a compact open subgroup. And therefore, we can think of it as acting here. And once again, there's a concrete interpretation for what the set of orbits looks like. The set of orbits of this action, or the set of double cosets, can be identified with the set of isomorphism classes of G bundles on X. Or let me write it like this. So this set is in bijection with G bundles on X up to isomorphism. So roughly speaking, what this theorem, what the function field analog of We's conjecture is about counting G bundles on algebraic curves. So more specifically, more precisely, what do we get if we run through the previous logic? Well, we learn that the Tamagawa measure of G of the adeles mod G of kx divided by the Tamagawa measure of the product of all of these G of OX's. Well, if this action was a free action, we would expect that just to be the number of G bundles on X. But since the action is not free, we have to count them with the appropriate multiplicities. And what this is the sum of overall G bundles of 1 over the size of the automorphism group of P. So conjecturally, the numerator of this expression is supposed to be 1. That's what We's conjecture says. So we're wondering, is this 1 over the Tamagawa measure of the product? All right, so now I want to take advantage of the fact that we're in the function field case, which should be easier than the number field case, because there's more structure. So in the number field case, we were counting quadratic forms in the genus of Q. Those formed a set, but you couldn't say much about the structure that that set had. In this case, you can say a lot more, because G bundles on X have an algebrogeometric parametrization. You can talk about families of G bundles that are parametrized by algebraic varieties over FQ. So for that, let me introduce a bit of notation. So I'm going to write bun G of X for what people call the moduli stack of G bundles on X. So this is an algebrogeometric object that has the following universal property. It's characterized by the following, that giving a maps from an algebraic variety Y into this thing can be identified with G bundles on the product X cross Y. So in particular, if I want to study G bundles on X itself, then I want to study maps from a point into bun GX, or where a point means spec FQ. Okay, so I said that this is an algebrogeometric object. Technically, it's an algebraic stack rather than something like an algebraic variety. So what that means essentially is that we're not just thinking about isomorphism classes of G bundles, but we're also keeping track of the fact that G bundles can have non-trivial automorphisms. If we want to keep track of that, we need a somewhat fancier formalism. But if you're not familiar with the theory of algebraic stacks, just imagine that's some kind of generalized algebraic variety. And what we're trying to do is count the number of points that that algebraic variety has. So that problem is the subject of another very famous idea of We. So let me another story that We introduced. Let's suppose that Z is an algebraic variety over FQ. So it's something that's described by polynomial equations with coefficients in FQ. So then I can ask, well, how many solutions are there to those equations in the field FQ? So let me write that set of solutions. I'll call it Z of FQ. So FQ is a finite field. That's a finite set. And the question is, how many elements does it have? Well, the idea is, let's embed this in a much larger set. Let's embed this in Z of FQ bar, where FQ bar is an algebraic closure of FQ. So this is now probably an infinite set, but it's an infinite set that has a lot of structure. This is an algebraic variety over FQ bar. So if you wanted to describe FQ as sitting inside FQ bar, you could describe it as the set of elements in FQ bar such that x to the q is equal to x. And there's a similar description of this of this set here, namely there's a map from this algebraic variety to itself, which just raises all coordinates to the qth power. So that map is called the geometric Frobenius map. I'll just call it phi. And when do all of your coordinates belong to FQ? Well, that's true if and only if you're fixed by this geometric Frobenius map. So what you're trying to count then is the number of fixed points of this map. And Wei's idea is, well, you ought to be able to figure out the number of fixed points by applying the Lefschetz fixed point formula. So the Lefschetz fixed point formula would suggest, so idea that the size of this set, Z of FQ, should be given by some kind of alternating sum of minus 1 to the I times the trace of Frobenius on the ith cohomology group of Y, where if Y is non-compact, we should use compactly, of Z. If Z is non-compact, we should use compactly supported cohomology. Okay, so this was an idea, and one of the great successes of the Grothendieck school of algebraic geometry was making sense of this precisely and proving it. And in particular, that meant defining what you may mean by the cohomology of an algebraic variety over a field which is nothing like the usual topological fields like R or C. So they introduced the theory of L-adic cohomology, and in particular, they proved, so this is an example of the Grothendieck-Lefschetz trace formula. So I want to apply this, but I want to apply this not to an algebraic variety, but instead to this moduli stack Bun-G. Now, if you want to do that, you have to be careful. So this moduli stack Bun-G, you can make sense of its L-adic cohomology, but the first thing you should be careful of is that that lives in infinitely many degrees. And therefore, there's a convergence issue when you write down a sum like this. And if you want to add up an infinite collection of numbers, you better be sure that the numbers are getting smaller and not getting bigger. So in particular, well, the analog of this trace formula, it's convenient to write it in a slightly different way. So let me just write what a trace formula would predict here. If you could apply the trace formula to an algebraic stack like Bun-G, what this would predict is that this is the sum, or some power of Q, times a sum over of minus 1 to the I times the trace of Frobenius on the homology of Bun-G. So that's not the only, this fact that there are infinitely many homology groups is not the only thing you have to worry about here. In particular, this doesn't follow formally from the Grothendieck-Lefschetz trace formula, and it's a big component of the story. But I don't want to talk about that component right now. Let me just take that as a given. Let's believe that this thing here is given by a trace formula, and that what you need to do is compute what the trace of Frobenius is on some homology groups. So then the question, Wei's conjecture, is a statement about what that trace is. It says that that trace is given by this, this left-hand side here. And what does this left-hand side look like? Well, if you unpack the definition of Tamagawa measure, it looks like a certain power of Q times something, a local contribution from every point of the curve, times some product over the closed points of the curve of some local factors that I'll call lambda x. And these factors of Q end up being the same. So what we're saying is that the trace of Frobenius on the homology of Bun-G is something that should factor as a product of a local contribution from every point of the curve. And actually a particular local contribution, but let me not get into the details of that right now. So why would you expect something like that to be true? Let me just give the idea. So an example of something that you could take G to be is the general linear group. And then G bundles just mean vector bundles. So in ordinary topology, when you first learned what a vector bundle is, you probably had something like an informal description. A vector bundle on X is a continuous assignment of a vector space to every point in X. It's a family of vector spaces parametrized by X, where the parametrization is in some sense continuous. And you could describe G bundles in the same way. What's a G bundle on X? Well, it assigns to every point a G torsor at that point, and those G torsors have to also, in some sense, vary in a continuous way. So let me just write that informally. I'll put this in quotation marks. Bun GX should be like some kind of continuous product of to specify a G bundle on all of X, you have to specify a G bundle at each point of X. And those bundles should vary continuously in some sense. So suppose that instead of being some kind of continuous infinite product, we just had an ordinary product decomposition with two factors. Well, then the homology of Bun GX would just factor as the tensor product of the homologies of those two factors by the Kunneth formula. And then if you wanted to compute the trace of Frobenius on the homology of Bun G, you would just have to compute the trace of Frobenius on the individual factors and multiply them together. So if you imagine that you could do something like that with this thing in quotation marks, it would read that the trace of Frobenius on the homology of Bun GX was something like a product over points of X of the trace of Frobenius on the homology of Bun G of this point. So what you have to make sense of is what do you mean by an infinitary Kunneth formula? In what sense is it true that the homology of Bun G factors as some kind of infinite tensor product of local factors? So that's where Dennis comes in. Dennis will tell you about that in the next hour. I think I'm good. I don't think so, because what's Bun GX, right? You should think of this as this is, if you think complex analytically, then this is like specifying a smooth G bundle with a holomorphic connection. And in one dimension, you don't have to say that the holomorphic connection is, that you don't have to say that it's integrable. So, and what's important is that the homotopy type of that is the same as the homotopy type of just smooth G bundles. Like having a holomorphic connection doesn't change anything because it's sections of some affine bundle. But in higher dimensions, there's an integrability condition, and you just have no idea what. I wouldn't expect you to be able to say anything. Okay.
In terms of what they did here, in what you described, that's all known to Tamagawa. What Tamagawa couldn't do, he couldn't find a proof, independent proof that the Tamagawa number is 2. And that's why he told me he didn't publish it. He showed it to Ray, and Ray wrote that book. But Ray, in the book, does give a proof, a separate proof, to Siegel, that the Tamagawa number is 2. The discussion of this equivalence that you described is in a paper of Bay, as also a paper of Knazer, which is but Bay's contribution really was to give the right name. and to give a separate proof. Tamagawa himself also has a Siegel number.
Other comment or question?
So, do you have similar conjecture for algebraic curve or complex numbers instead of finite field?
So it's true that the thing that Dennis is going to describe is a precise formulation of what it means for the homology of Bun G to factor as an infinite tensor product. That makes sense over any algebraically closed field, say. And then when you specialize to the fact when you come from a finite field, then you can take the trace of Frobenius.
No further questions? Let's think.